So our next and last speaker for the day is Mike Ward. He's a director of consumer entertainment technology at Dolby.
Testing, 1, 2. There we go.
Okay. And he will be talking about coding and system approaches for next generation audio. If his file will come up. Yeah.
There we go. All right. I'm painfully aware that I'm standing between you and the bar. I will make this as quick, informative, and painless as I possibly can. Okay. So a slightly different spin. I wanted to come at this more from how Dolby's been approaching next generation audio, some of the problems we've come up against, how we develop the systems, and give you an insight on where things are. So similar to Neil's presentation, which is really good, these are kind of the 4 pillars of immersive audio or next generation audio that we see. So accessibility, we want to make this audio accessible, descriptive audio, dialogue enhancement, personalized, so you can choose the audio presentations that you would like. Immersive, we want to give you a more immersive experience, so that includes the height component, but also to do that in ways that don't just require you to buy hundreds of loudspeakers. You can do this in a more reasonable form factors, and also adaptable. And this really refers to customization for consumer playback, for the devices, the environments, how many speakers you have, how big your living room is, how acceptable it is to your spouse, which is another really big aspect of this. With respect to the functional components for next generation audio, encoding, decoding, rendering, and metadata are really the 4 fundamentals that we're working with and building with. I did want to sort of outline, the title for this presentation was Next Gen Audio. To some extent, we're here already a little bit. We haven't delivered all of Next Gen Audio yet, but the immersive and adaptable bit is kind of available today in quite a lot of services. So this is just a sort of quick illustration of these guys are on air or online today with production services delivering immersive audio using Dolby's audio formats. More to follow. We also have active trials with immersive audio for ATSC3 transmission happening in North America, because AC4, as you probably know, is the required audio format for NTSC3 for North America. And other recent events with immersive audio, the FIFA World Cup actually produced and distributed with immersive audio. Winter Olympics, NBC, we work closely with them to deliver in immersive audio. And the French Open, as Niels showed in his presentation. We also did a Dolby AC4 presentation to mobile phones for that event. Okay, a little bit on audio coding. This is going to make you all wish you'd started drinking, but again, I'll try and move it fast forward as I can. So we need to code audio because it's not as bad as video, but the bit rates for audio are too high to get to consumers in a lot of ways. So we apply perceptual audio coding to the audio signals. We take advantage of 2 key properties of audio signals: redundancy, there's similarities in signals across time or frequency, and also irrelevance. Some audio signals have no audible consequences. You can see in this little diagram here, we have a audio envelope, or envelope of audio signals, and we have a masking curve, which means that audio around those original spectral points can't actually be heard. So that's immediately something we can take advantage of when we code the audio. And so when we develop a codec, we can look for these areas under the masking curve and apply coarser quantization, which allows us to deliver lower bit rates. So that's kind of the very fundamental basic principle of lossy perceptual audio coding. For a number of reasons, pretty much all the really efficient audio codecs are all frequency-based, frequency domain-based, not least because the human auditory system is frequency-based, and we can take advantage of the limitations, weaknesses of the human auditory system and hence code more efficiently according to that. Another aspect of perceptual audio that we need when we get to the very, very low end of the audio bit rates is a sort of a different approach to coding, is this thing called parametric coding. So traditional coding uses what's called waveform coding, This is a quantized representation of the original audio waveform. But to get to really low bit rates, we need to use a thing called parametric coding. What this is a, rather than this verbose description of the waveform, it's parameters in the bit stream, very low parameters, to inform low bit rate parameters, to inform the decoder of how to get from a waveform, how to get from an original waveform to a sort of construction of the original audio in a very low bit rate fashion. Two of the prevalent coding methods that are used for parametric audio, high frequency reconstruction. So you may have heard the term spectral band replication, SBR, or spectral extension. This takes advantage of the fact that a lot of times in audio you have a harmonic relationship between low frequencies and high frequencies. It is possible to parameterize that relationship. So rather than delivering high frequencies in a verbose fashion, which is very data rate intensive, you can deliver the low frequencies and information to tell the decoder, based on these low frequencies, here's how you construct the high frequency envelope very efficiently. Another aspect that you can take advantage of, and with immersive audio we use this a lot, is spatial channel coding. So if I have, in a simple example, stereo audio, quite a lot of the time there's commonalities between those left and right channels. I can code those commonalities quite simply. And I can do a lot, again, with parametric coding in that respect to say, well, from this left channel, you can create this aspect of the right channel, again, very efficiently in the decoder. Multiply that by a lot of objects, and you can start to get a massive data rate reduction. So those are the principles that are used fundamentally for, that we've approached coding for next-gen audio that allow us to get to very efficient data rates. If we take a little look at AC4, which is our newest generation technology, this is a multi-domain audio system. So we're actually using two frequency domains to code the audio as efficiently as possible. MDCT domain is used for waveform coding, and then the QMF domain for parametric coding. So in the MDCT domain, we have different quantization methods depending on whether your content is general audio or speech. And we have some specific coding tools, optimizations for stereo coding in the MDCT domain. The real complicated and very efficient stuff happens in the QMF domain. And this is where we're really pushing the boundaries on audio coding. So, for example, in the QMF domain, we can apply temporal shaping of quantization noise. We can move it around in time, depending on transient events, masking, things like that. As mentioned, we can do high-frequency spectrum reconstruction, so from a low frequencies, synthesize high frequencies. And we can use parametric spatial coding tools for efficiently coding the differences between channels and objects. And I'll come on to the other blocks later. So from a sort of bitrate range of operation for AC4, we're looking at pretty low bit rates. So from stereo, 32 kilobits per second. And then for immersive audio, we can actually deliver fully immersive audio as low as 144 kilobits per second at really very good quality. So highly efficient. And we would like immersive audio to not be impacting on the bitrate budgets that everyone is so concerned about. So that's what we're working on to improve and enable. Okay, so that was a whistle-stop tour on audio coding. Next. I want to talk a little bit more about next-gen audio system design, because the coding is just one portion of next-gen audio. Taking that coding engine and then using it in a flexible way to actually deliver the next-gen audio experience is also very key. So starting with immersive and adaptive audio. Nils already talked about this a little bit, and I wanted to highlight it as well because it generates different problems as a codec and system designer. Live mixing environment and practices and the amount of flexibility you have is very different to mixing for post-produced content. So post-production, we've sort of enabled the flexibility for the audio mixers to manage an awful lot of channels and objects. So for the immersive audio format that Dolby has, Dolby Atmos, the typical construction of the mixes is a 9.1 channel bed, we call. It's the bed of the mix. It's what the mix is based on. And that's a 7.1 in the surround plane with two overhead speakers, and then up to 118 objects. So 128 in total. That's an awful lot of audio to be managing, but in that environment, you can actually do that. And what we're doing basically is taking an entire mix session and exporting that for playback, either in the cinema or to get it to the home. And as it says here, it's really, we're not constrained here by real-time requirements or infrastructure limitations. We're just limited by file size, but for all you video guys, you're like, yeah, whatever, doesn't even register. On the live side, live mixing is just panic all the time. You're mixing everything in real time. You have unexpected things happening. You can't be dealing with hundreds of objects at the same time as that. So the live mixing right now is sort of evolving from surround mixing. They've not unreasonably said, okay, it's not a huge stretch to add some height speakers to our surround speakers. So typically, it's a 5.1.4 channel bed, so an immersive channel-based mix. And then a small number of usually static objects for specific audio elements. So for example, I can have separate dialogue objects. I could have commentary objects, specific dialogue for different languages, things like that, but a lot less complex. As an illustration, this is a picture of a full Dolby Atmos mix for post-production that would be run in, for example, Pro Tools. As you can see, this actually does have 128 objects, and that's just showing the channel-based buses and then where the objects are in the mix at that time. And we have a 3D panner here which shows the representation of where all those objects are. On the live side, significantly simpler. So this is a live mixing tool that is being used today for a lot of the Dolby Atmos live production. In this case, you have a 5.1 channel bed, four height channels, and then in this case, an English and a Spanish commentary. A lot easier to deal with. A little bit on interchange standards for NGA, as we are now dealing with PCM audio, or we're dealing with audio plus metadata. The sort of existing standards don't really support metadata for audio that well. So there's a lot of work and standards work happening that we're engaged with to make that a reality. So on the post-production side, a lot of the work we've been doing has been in the ITU. There is a standard there, the audio definition model, which is a way of describing immersive audio, personalized audio in a very comprehensive fashion. Marry that with the broadcast wave standard, and then you can deliver a full immersive audio program in a wave file. And as Annie mentioned, there's also now work happening in SMPTE as part of IMF to define an immersive audio bitstream format that will be used for interchange there as well. On the live and real-time side, there's a couple of activities happening. There's work in SMPTE for audio metadata standards, under SMPTE 2109. Additionally, in the ITU, there's also work happening on a serialized version of the ADM standard, which will allow for real-time delivery of ADM. Okay, so we have 128 objects and lots of metadata, and we have 100 megabits per second of audio. How do you get that to the consumer? It's a little bit beyond most people's bandwidth connection to the home. And again, video's there. We're not going to get all this for audio. Never happens, unfortunately. Well, there's a lot we can do, actually, with this object mix to squish it down, which is great. First one is pretty easy. Turns out, if you look at a mix, not all beds and objects in a mix are active at the same time. This is a little bit of an eye chart, but I did some analysis on some movies, some immersive movies, to see total object count versus actual simultaneously active objects. And as you can see, it's actually, in some cases, for a large number of tracks that are present, the number of simultaneously active objects is actually fairly low. So there you get instantaneous data rate savings, which is great. But not always the case. If you look to the far right, the movie at the far right there, 79 tracks, 74 objects active at the same time. Very, very complex mix. Not something you can just throw away. Anyway, first step is easy. There's built-in redundancy in these mixes. We can take advantage of that. Step 2 is a bit harder. But we did a lot of work on looking at mixes and how we could, again, simplify and reduce the number of discrete objects and elements that were in the mix. Turns out if you look at the relative position of objects and their relative loudness, you can combine these objects into a single PCM track, and again, significantly reduce the number of objects that you have to deliver to the consumer, to the home. So we can go from, say, 128 down to, say, 80, and then the output of this process is somewhere in the region of sort of 11 to 17 objects, which is then much more feasible to get to the home. So once we've done our spatial coding, as we call it, we can then encode it. And this is a quick block diagram of what the AC4 encoder looks like. The input, we have our spatially coded objects. And in the case of AC4, we actually run spatial coding again inside of the encoder. The reason is that AC4 is a scalable solution. We always have a core bit stream or substreams, and then we have sort of extension data on top of that. The reason for that is for decoding complexity. For some decoders that are not going to feed a fully immersive system, we can give them a core, which is simpler to decode. And for decoders that are going to be connected to a 714, 916 very high-end home theater, they can take advantage of the full capabilities of the bit stream. So another characteristic of object audio, well, PCM plus time-varying metadata. You have to have metadata to describe what's going on. So in this metadata, we have timestamp. You need to know, where this where this object is going to be at any one time, and also where it's going to go. You need its position. And then we also give the content creators a bunch of controls over what they're going to do with those objects. So, for example, the content creator can say, this object, I don't want it to go to these speakers. A good example of that is if I have an object at the front of the room, I want to fly it to the back of the room. I may not want to use the sidewalls. I may want to just go through the overheads for helicopters, airplanes, things like that. So we can allow people to exclude speakers' masks if they wish to do so. We can also let content creators sometimes want to snap an object to a particular speaker, so we can enable that as well. It's possible to have an object that has size. So rather than a point source, you can expand the object out so that it's rendered from multiple speakers simultaneously. You can also add a correlation to that process to add reverberation to the experience. And additionally, if you are going to do personalization, that also adds presentation and interactivity metadata into the mix. And once you have all that, you need a renderer. Now, the renderer is very, very key for next-gen audio. This is the component that converts all of those objects and the metadata associated with them to the rendering environment that you have. Could be as simple as stereo speakers or headphones. Could be as complicated as a multi-channel loudspeaker system with multiple heights, surrounds, and everything else. The job of the renderer is to understand the environment that it's in and to take the audio that's coming in and map that to the environment in the optimal way. So in the case of next generation audio and case of the Dolby formats, what we want to do is to provide a single bit stream that can be customized to all of the playback environments. So a very simple example is taking objects, mapping them to different speaker locations. Another aspect that we understand needs to be taken into account is playback loudness. So as part of rendering this audio, you need to understand the environment that you're rendering to. If I'm listening on a mobile phone, on a train, the ambient noise level is going to be very high. I need to be able to compress the dynamic range and increase the output level so that I can actually understand what is going on. But that same experience on a loudspeaker system in my living room, or ideally my home theater room, if I'm lucky enough to have one of those, you don't want that experience. You want the full dynamic range. You want the full impact of that mix. So inside of the bit stream, we include playback level as well as dynamic range control metadata, all controlled by the content creator to define how that playback experience is going to happen for these different listening environments. Another aspect that object audio gives us an advantage over, over traditional, is for binaural rendering. So that's the process of rendering a sort of virtualized experience of immersiveness for headphones. It turns out you can do a better job with that if you have objects rather than trying to simulate loudspeakers. So you feed objects into the system, you get a better binauralized, virtualized experience. So if I go back to my AC4 decoder diagram, we have all our coding blocks there to make sure our data rate is as efficient as possible, while our quality is as high as possible. We also need to add some other blocks. And this is really the key one, is our renderer block here. So this includes rendering, dynamic range control, as well as dialogue enhancement. Another aspect of the environmental playback is, can I hear the dialogue? As a user, maybe I want to increase the level of the dialogue or duck the level of the ambient sound to make it more intelligible. And one other thing we added is video frame synchronous audio framing. So AC4 you can actually run at the same rate as the video, which is, if you're trying to do ad insertion or anything like that, is a nice feature. It makes splicing an awful lot simpler. All right. So that was the immersive and adaptable piece. Now I want to talk a little bit about accessible and personalized. I would say the immersive and adaptable piece is here and now. This is stuff that's already happening today. Accessible and personalized from an end-to-end perspective is in the works. Content in some places is starting to be produced with accessible and personalized audio in mind, but the whole chain, that's a challenge. So the goal here, we want to use the NGA system to enable a personalized audio experience for the user when available, and also to enable accessibility. So this is multi-language delivery, it's audio description, and it's dialogue enhancement. And additionally, again, similar vein, is this ability to select different audio experiences depending on what you want to watch. So team-biased sports commentaries, alternate languages, director's commentaries, things like that. I would point out that a lot of the features there, the selection of different audio elements, is not really new. It's been around for a while, but it's the combining that with immersiveness that's sort of the part of the NGA package. It's bringing everything together is what we want to get to. So on the right is a sort of is a demo UI that we've had on the Dolby side for showing how you can pick different presentations from a single audio bit stream. Our experience at the moment working with TV vendors, things like that, is that they want something a lot simpler from a UI perspective. So language selection is going to be based most likely off the language selection that your TV has as a system. The reality of doing more complicated things with the TV remote has yet to be proven. If you have a phone, a tablet, things like that, it becomes easier. But yes, the UI for NGA is an interesting topic. So if I go back to my immersive audio, my groups, my objects, I can take that principle and apply it to this personalized audio process. So here I have various components of an audio mix. I have music and effects, which you'll hopefully is common. And then I have dialogue elements and then commentary elements. For example, 11 to 15 immersive music and effects, and then a smaller number of dialogue clusters. Dialogue is typically 1, 2, or 3 objects worth of audio at one time. Using these building blocks, I can build up these different presentations. So here I'm using the music and effects with English dialogue for an immersive English presentation. I can choose to add audio description to that, or a commentary, or I can choose music and effects with a separate dialogue helper track, which is to match the Spanish dialogue. And again, this can all be done with immersive audio in a very efficient delivery pipe. With respect to the sort of AC4 system integration, this is how the interaction is designed to work. So before the AC4 decoder, in the AC4 bit stream, we had this thing called a table of contents, which describes all of the presentations in that audio bit stream, what their languages are, what the type of presentation is. And that information is provided to the playback device. And then the playback device, either based on system settings or based on the user, will pick the appropriate presentations from the bit stream and tell the decoder, please decode these. And the AC4 decoder will then decode those, send those to the renderer, and produce the, again, optimal presentation for that output. All right, ooh, well ahead of time, that's good. That's the end of the presentation, so any questions, please, but I guess otherwise everyone's going to go to the bar.
Any questions from the audience? I'm not seeing that, Mike.
Didn't expect that to be.
Okay.